currently in the Mellanox Networking at NVIDIA. He serves also as the chairman of the HPC-AI Advisory Council, and he has been a member of IBTA and contributors to a lot of the specification. He holds multiple patents. He's a recipient of the 2015 R&D 100 Awards for his contributions towards the core direct in-network technologies. And recently, last year also, the UCX also got an R&D 100 Awards. So Gilad, please share your slides and the floor is yours.
Thank you, DK. Can you see my slides?
Yes, yes.
Hear my voice? Cool. First, thank you very much for hosting me on this virtual MUG conference. And I do hope that next year we'll be able to go back and meet in Ohio.
Sure.
And continue to collect those mugs, by the way. That we're
sorry, this year we could not do, we were thinking of doing a virtual mug. Okay.
Yeah, exactly.
Yeah.
And it's definitely an honor to present after you, DK. So, thank you very much. I think your presentation was very interesting. A lot of new development, a lot of new things. So it was great to see that progress.
Thank you.
I'm going to talk about the networking piece and focusing on the InfiniBand technology. And we'll go deeper as we move ahead with the presentation. First, the way that we look on the network or the concept of high performance computing, it's much broader than just looking on the supercomputer by itself. The scientific or the new scientific world is being expanded actually to start including edge computing. Devices that can, or appliances that can bring computing to the edge and actually be able to do the first data analysis next to the sensors and then move in a very effective way the results or the analysis from the sensors into the storage or other big data appliances or into the supercomputer for doing further simulations and further analysis. So it's not just the supercomputer by itself, but we're looking on the scientific computing as something that includes more and more elements. And obviously you need a good network or advanced network to connect at the edge, to connect between the edge and the different elements, to connect the supercomputer by itself and so forth. When we go into the supercomputer, essentially there are three main elements there. The CPU, the GPU side, and the network, which we call DPU. The network has been transferred from just being a pipe that moves data from one side to another side to an element that provides processing capabilities. The network actively participate in the job runtime. It was great to see some of the slides from UDK that talks about the capabilities of Sharp, which is part of the computing engines, tag matching and things of that sort. So obviously you want to keep the speed of light on the network and to move in the right speed and low latency. But if you want to overcome the bigger issues in latencies, you need to actually have the network participate or actively participate in the job runtime. And there are two kinds of DPU units within the network. They are predefined or pre-configured DPUs. Those are data processing engines that are built for a very specific mission. And there are programmable DPUs, which are compute engines that can be programmable, either by writing C code and compiling that, just running Linux on the compute engines, or running other kinds of languages on compute engines that sits on the data path within the different network devices. So a few examples of those data processing units. For the programmable elements, you can find today ARM cores, for example, or there would be other kinds of compute cores with memory next to that, or MMUs, that can be used for pre-processing of data, can be used for hosting user-defined algorithms to be able to actually run algorithms on the data when the data move within the network. And that's something that people can use for pre-processing of information, or moving control paths of applications, moving storage operations into the network, and actually have the network be able to do that. We have devices today such as Bluefield for InfiniBand that includes multiple cores of ARM with memory attached. So you can actually have a Linux machine within a Linux machine. There will be generations of InfiniBand devices that include different kinds of cores, heavier, less heavier, different kind and sizes. On the pre-configured DPUs, we can start to find compute engines that their mission is to migrate communication frameworks from running on the CPU to run completely on the network. So Sharp is one example, which is moving data reductions to be actually done and executed on the network level. MPI tag matching is another example, where you move the matching, or the part of the matching process into the network. Shield is an element that utilizes computing engines to calculate topology-aware actions that can be used, for example, for resiliency of the network. There is accelerations around storage or fast storage, around security. You can not just bring isolations between jobs, but you can actually do encryptions of specific data on the network. And with that, you can completely isolate and encrypt part of a supercomputer for running personal-based data simulations and things of that sort. In the future, we'll actually see that majority of them, or most of communication frameworks, if it's MPI, SHMEMPIGAS, UPC, NICL, ACCL, whatever, actually runs completely on the compute engines on the network and not running on a CPU or a GPU in that sense. The last part of the network is obviously the speed of light. InfiniBand today runs in 200 gigabit per second end-to-end for the second year. So it was the first one to do 200 gigabit per second end-to-end. It will be the first one doing 400 gigabit per second end-to-end with very extremely low latency. There is nothing that get close today to the InfiniBand latency. We're talking about switches that runs in 100 nanosecond. We're talking about adapters that runs in 150 nanosecond latency. Nothing get close to that. InfiniBand, just in a pure latency, it's easily 2x, 3x lower latency than Ethernet or anything else that exists or will exist. Beyond of that, you have the most efficient RDMA, which is 30 to 40% more efficient than Rocky, for example. As Rocky is kind of took portions of the InfiniBand RDMA, but it could not do the complete RDMA as InfiniBand. You have the GPU direct RDMA or GPU direct storage or GPU direct async and other things. Adaptive routing, another unique value of InfiniBand that doesn't exist really on Ethernet is another example. And then you have congestion control and be able to support smart topologies and things of that sort. But the more important part of the network is actually the computations that exist. I think InfiniBand is probably the leading one of bringing compute into the network. And that compute mission on the network, beyond of hosting user-defined algorithms, is to key latencies. And key latencies of MPI operations, which are measures in tens of microseconds, for example, and not the low-level network latency. There is an ongoing effort nowadays within the UCF, or the Unified Communication Framework Consortium, to build and specify a standard API, which is called OpenSnappy, that will enable users to migrate algorithms on a standard API or a standard interface to any compute engines that exist on the network. if it's a compute engine that sits on an adapter card, on a switch device, if it's a ARM core or a different kind of core or a specific or predefined engine. And with that Start API, you can get access to different kind of services on the network, different kinds of analytics on the networks, be able to migrate storage functions, compute functions, communication functions, and security functions, and more, management functions as well, that today runs on the CPU into the network, as the network is much more scalable in the reach to the different processes and is much more immune to system sizes. Some of the key advantages of InfiniBand are actually coming from the core of the InfiniBand technology. InfiniBand is based on 4 main fundamentals. The first one is very smart endpoint. InfiniBand does the full transport on the network, the full transport, not stateless offloads, or the full transport runs on the network, which means you get maximum of CPU cycles or GPU cycles dedicated to the application. And then you can do smart elements or smart algorithms because you sit close to the CPU memory, to GPU memory, and you have your own memory. The switch architecture was designed for scale. The switch network is very simple. It was actually designed to be simple to the extreme. If you are taking an Ethernet switch, for example, every Ethernet switch comes with a server inside of it that runs the operating system of the switch, which increase the cost of Ethernet switches. If you look on InfiniBand, InfiniBand does not have a server inside of the switch. It's much more cost effective from a networking perspective. And because InfiniBand was born as a pure SDN fabric before people knew what SDN, you can build any sort of topology, you can control all of the routings, you can optimize the system to the workloads. As well, you have centralized management. You can control everything from one place. And the last part, of course, InfiniBand is a standard. So it's a full backward compatible, full future compatible. You can connect future generations to past generations, and everything can carry, by the way, the same software drivers. On the HDR perspective, I think InfiniBand HDR, the 200 gigabit per second of InfiniBand, is demonstrating the fastest adoption rate compared to any other previous InfiniBand generation. Several reasons. One of them is we're seeing growth in HPC space. InfiniBand was already being used last year to connect systems in a size of 300 petaflops and 400 petaflops, which unfortunately are not listed on the top 500. But we're seeing that scale continue to increase. We also see a move from proprietary network towards InfiniBand. ECMWF is a great example. DKRZ is another great example, and there are many others. We're also seeing a nice adoption of InfiniBand into the cloud. In Microsoft Azure, it's a great example of leveraging the 200 gigabit per second InfiniBand to bring the best performance in the cloud, completely the best performance in the cloud. And not just that, InfiniBand is starting to become the de facto for deep learning. I'm not sure if you guys saw, but there was a blog from Microsoft that talks about OpenAI utilizing InfiniBand for their system. We're seeing InfiniBand adoptions going to more hyperscale infrastructures for compute and data intensive applications. So it's great to see that InfiniBand is expanding not just in HPC and taking the place of proprietary networks, but also expand into deep learning very strongly, as well as into hyperscale infrastructures. So if you think about the different engines, Sharp is not a new thing. There was also a tutorial about Sharp yesterday. Sharp was one of the first compute engines that were added to InfiniBand, and it's unique to InfiniBand. You don't see that on Ethernet devices or other proprietary protocols in that way. Sharp had or has two generations to date. Sharp, the first appearance of Sharp was on EDR, where it's enabled to do data reductions on the network, on the switches. So the switches collect the data doing reductions, then forward it to a top of the switch in the tree that does a reduction among the entire switches, and then send the results back to the host or to the processes. The first generation of Sharp on EDR was focused on small message reductions. The second generation on HDR added ability to do large message reductions, and that's for deep learning. And in the next generation of InfiniBand, the NDR 400 gigabit generation will have the third generation of Sharp, which will include more capabilities for data reductions. What does it give? On one side, flat latencies. So when you're doing reductions, you can easily get to 30, 40 microseconds on 100 nodes or alike for doing reductions. And there is nothing you can do in order to cut it down. And if you're running reductions on the CPU, the more processes you add, the higher the latency is. InfiniBand gives you flat latencies. That's one thing. No one else can give flat latencies for that. And I think DK also showed an example of those flat latencies, which is great to see in other testing results. We run Sharp on the University of Toronto, which is, I think it's still today the fastest supercomputer in Canada. On the entire system, 1,500 nodes, 40 processes per node, so a total of 60,000 MPI ranks. Cut the latencies by 7x. And it's not just the latency, because once you do reductions on the network, you also reduce data motion, which is another benefit. And obviously, deep learning, it's all about reductions. So this is a recent result running on part of Selene. Selene is the top 7 supercomputer that was built in 3 or 4 weeks, including a lot of DGX boxes and a lot of InfiniBand Connect X6 and HDR switches. So this is running on a section of Selene, looking on the sweet spot of message sizes for deep learning, and then comparing Nickel over InfiniBand versus Nickel over InfiniBand with Sharp. So Sharp gives here 2.5x performance improvement for deep learning, for reductions operations for deep learning. The other predefined engine, it's the MPI tag matching. The way that it works is that the Connect X6 adapters include the tag matching engines. The software or the user posts buffers with tags, and that posting or that list actually is accessible by the network because of the network device. So when a network or message arrive from the network, an MPI message arrive from the network, the adapter does the matching. And if there is a matching, it's going to go as expected a message, and either the hardware or the InfiniBand adapter will place the data or scatter the data to the local buffer. And if it's a read message, if it's a rendezvous, it actually is going to go to the other side, gather the remote data, and then put it in the local buffer. All done by the hardware. Unexpected messages will go through a handshake to the software and will handle by the software in this case. So everything that is expected message will completely be handled by the engines on the network. So those slides I stole from DK. So courtesy, I think he showed them slides, so I don't need to repeat. But it's nice to see almost a 2x performance improvement, and this is testing that runs on DAC. And it's actually 2x, almost 2x, so 1.8x performance improvement on 1 to n nodes, and it carries all the way to 1K nodes, and I assume that it will run on larger, we'll continue to see the benefits. But it's not just cutting the latencies, it's also the overlapping. So overlapping is a key thing, and tag matching plays an important role in enabling overlapping between compute and communication. And here with tag matching, you can get to the 100% or nearly 100% overlapping, which opens an ability to start using asynchronous modes in much more frequent and be able to actually accelerate application performance even further. GPU Direct is not something new, completely not something new. And those are some examples also from DK that shows the reduction of latency all the way to 1.85 microsecond for GPU to GPU communications over the network. The interesting part is taking that and applying that again to accelerate deep learning. So there was a nice paper released by Facebook that talks about deep learning training in the Facebook data centers, which compare running ALLREDUCE scale out on InfiniBand with GPU Direct or without GPU Direct, and they demonstrate up to 3x performance improvement for that. Then part of the network is obviously quality of service. InfiniBand enable different engines or different capabilities for quality of service. For in-network congestion, InfiniBand offers adaptive routing. And it's advanced adaptive routing that doesn't exist in other networks to solve the cases of point-to-point. And then there is in-cache congestion, which is many-to-one. And for that, you have the congestion control capabilities that includes fast detections on the switches and a fast indications to the adapters or the network adapters to take those specific flows, those specific many-to-one flows, and reduce their injection rate to what the target can handle, and with that to eliminate congestion control or eliminate congestions in cases of many-to-one. There was a nice paper comparing the adaptive routing versus static routing capabilities of InfiniBand on Summit, running MPI graph. With static routing, you can see the spread of data. So not all of the MPI pair of processes getting a full bandwidth, but with the InfiniBand adaptive routing, which is today is a default in any InfiniBand installation, the network actually balanced the traffic evenly, completely across all the network. So you get very close to 100% network efficiencies for point-to-point communications. On the congestion control is definitely not something new to InfiniBand. I was excited to participate in writing a paper back in 2010 that released the first results of congestion control in InfiniBand, and actually showing how the congestion control eliminate victim flows and enable even spread of many-to-one traffic over the network. Recently, we run the GPCnet benchmark, which is a synthetic benchmarks that looks on congestion control or congestion factor, running 3 different tests, if it's the random range latency, bandwidth, or reduced latency. And you can see the difference within disabling the congestion control or keeping the congestion control. With congestion control, you get a congestion factor of 1, not just for the average, but also for the 99%, which means that the performance with congestion or performance without congestion is the same performance. So combining everything together and taking the 4 major elements, I think, of InfiniBand. First one is speed of light. You have 200 gigabit per second end-to-end. We'll go to 400 gigabit per second shortly, end-to-end. It will be the first one doing that. RDMA, GPU Direct RDMA, GPU Direct Async, GPU Direct Storage. Latency, ping pong latency, nothing get close to that. Nothing get close to InfiniBand. Even more than that, it's not just the adapter latency, which is better than anything else, including Ethernet, but it's also the switch. There is no switch in the world that get close to the latency of InfiniBand on the switch. Nothing get close to that, which means the bigger the system is, the bigger the latency advantage of InfiniBand will be. So that's one element, the speed of light. Second thing is sharp. So SHARP becoming more and more important as part of moving data reductions to the network. For MPI, for Schmempigas, for deep learning. And SHARP was the first element. Now you have MPI tag matching. We will see more predefined engines that will move more operations of MPI to the network. And actually, Invapid from DK will not run on the CPU. It will run completely on the network. Or complete data path of MPI will run on the network itself. And then actually, you can also move the control path into the programmable cores that exist on a network with the memory next to them. So actually, that's going to be the future of communication frameworks. I didn't touch about Shield. I think I presented it last time. That leveraging the engines on the network to increase resiliencies. So the network elements can have communications between them. It talks about the conditions of the network. And where do I want to move the data, where I don't want to move the data, how to find better paths, how to avoid issues within a fabric, and actually be able to bring the first elements of self-resiliency into the network itself. And the other part is the UFM Cyber AI. It's an appliance that we announced a few weeks ago, which combines a very rich telemetry from the network with deep learning algorithms. And I think that's probably the first platform that combines the networking aspect of Mellanox and the GPU aspect from NVIDIA to actually build a platform that takes or collect rich telemetry information, apply deep learning algorithms on that to learn the data center operations, and with that to be able to predict failures before they happen, and with that to enable improving OpEx and enabling the IT folks to fix things before they break. But not just that, also to bring security into supercomputing. That appliance learns the communication patterns of jobs. It learns the fingerprints of jobs. So if someone is running a new workload, which could be forbidden, but a new workload, the IT manager can get an alert and actually make sure that the approved workloads are the ones that are running on a supercomputer. Anyway, I could have probably talked a lot more about the things on the InfiniBand technologies and the advantage of that. But thank you for listening, and I'm gonna stop sharing just to see if there are.
Yeah, Gilad, there are 3 questions. Either you can take a look at the Q&A window, or I can read it out to you.
Yeah, let me look on the window. I'll just stop share for doing that. Well, DPU, does it mean that this architecture relies? No, it's not. You can also find DPU in Wikipedia and more places. I don't think you can actually trademark that, but in any case, if it's trademarked, it's trademarked. DPU refers to any data analysis on the network. It has nothing to do with what Mellanox is doing, has nothing to do with any other company technologies or IP. Everything that I mentioned here, it's completely Mellanox IP and not any other company. It's the same like trying to trademark CPU or try to trademark GPU in that sense. So that's the first question. Central management of InfiniBand, any possibility of distributed management? The answer is yes. You can do distributed management, you can do centralized management. There's a lot of tools that enables you to do both. By the way, for any questions that I didn't answer, feel free to email hpc@mellanox.com or to email me directly, which is my last name at nvidia.com, and I'll be happy to answer. Yeah, I'm not sure that you want to hear my impression on Slingshot GPCnet. I'll tell you what I think about GPCnet. I think GPCnet is a benchmark that was written because of a network vendor, because of a vendor wanted to highlight that that's the first time that they brought congestion control into their fabric, which I don't understand why to make so much noise about something that is common in other fabrics. Congestion control exists in InfiniBand for many years. It exists in Ethernet for many years. So from having company in 2020 coming and saying, hey, we have congestion controls, and making so much noise about congestion controls and creating a benchmark for congestion control, it's like having BMW coming out and announcing tomorrow that their new cars has really, really, really round wheels. So that's what I think about that. Now, GPCnet benchmark, you can use it if you want to look on the impact of congestion, assuming that 8 bytes are always the good flow and 4K bytes are always the bad flow, and 20% of the nodes are doing one thing and 80% of the nodes are doing another thing. Regardless of that, we have run the GPCnet benchmarks and we demonstrate better results than Slingshot. So people can decide what to do with that benchmark. Load balancing strategy. So I guess this refers to the adaptive routing element. InfiniBand adaptive routing is typically a local decision. We do have sure that actually enable information to pass between switches or between devices that can give feedback on adaptive routing or feedback on local adaptive routing decisions. Adaptive routing is being done not just on the switches, but also on the adapters, which is another value. You can extend it all the way there. And the switches has different kind of strategies that they can choose according to. You can go from a least busiest port to random selections among groups and ports and things of that sort. So there is a variety of options there. Energy consumptions and security metrics for adaptive routing. Well, definitely, if you utilize the network in a full balanced way, then you are running things much faster, and with that you can definitely consume energy. Security metrics, there's multiple things around that, but just because I'm 6 minutes over time, I guess, and I'm kind of holding your break, I'm more than happy to take that offline. Again, you can email hpc@mellanox.com, and I'll be happy to answer more questions offline.
Okay, so thanks a lot, Gilad, again. It's always a pleasure to have you talk here, sharing all the latest technologies.